Hello there, this is Fanjun over here, and I'm just recording a radio presentation, or actually just a experiment that we are running for Dynamics experiment, and my group members are Peru, Bowie, and David. Next is our first experiment.
So basis on that, we looked at the whole data and we averaged out certain values that we thought were not under influence by magnetic force. So the acceleration versus time graph for run one and run two, as you can see here, we have taken the flat-ish consistent trends that we thought are not influenced by magnetic force for run one and run two. These values for run one, so example 0.85 to 1.5 seconds, were averaged by summing values and dividing them, as shown over here. Same thing was done for our two other ranges. This is a table of all the three ranges we took and the average acceleration for all those three ranges. Then a total average acceleration for run one was produced 1.021 meters per second squared. Same thing was done for run two, but with slightly different time ranges because the trend was slightly different. However, we still took the most consistent values that were not influenced by external forces, and we found an average acceleration, 0.98624. These two accelerations were then combined to get a final theoretical acceleration of 1.004 meters per second squared. Now, for the mass of the cart and bumper, we assumed that the cart was on a frictionless track, assumed it was frictionless and a lightweight pulley, and acceleration in the vertical direction 0 for mass of cart plus bumper, and acceleration in the horizontal direction 0 for mass of the weight, as you can see in the FBD below. Tension force, this is the calculation. Tension force was found using some of vertical and horizontal forces, and then the same thing was used to get subbed in to get total mass of the cart and bumper, 263 grams. This is the whole working process to get that. Now, to calculate force, mass of bumper, we needed to calculate an average force. So we took the same time ranges by conducting a force versus time graph, and we saw that, yeah, around the same time ranges, but we didn't take the second and third ranges because we found out that, look, looking at the trend, they are influenced by magnetic force and they're not consistent with each other. It's slowly decreasing and decreasing. So we only took the first range, this first flat consistent range here, 0.85 to 1.5 seconds. For run two, we took all three ranges because, as you can see, all three trends are very consistent with each other. So this average was also found to get 0.0254 newtons. Average force of run one was found. Average force of run two was also found. To get that, we got masses by using F equals ma for both run one and run two, and then average those masses out to get a total mass of the bumper, 27.6 grams, and therefore the mass of the cart, total minus bumper, 235.4 grams. Now, comparing to our measured data, we found an average acceleration. We know that our theoretical acceleration was 1.004. Now, if you look at this range over here, it's slightly higher, and this is due to the assumptions we made. In reality, the track when pulley will not be frictionless, and there will also be a degree of aerodynamic drag. This was the formula we used to measure from a theoretical to experimental. Now, using that formula, we can see that the trend between our estimates and our the experimental data for acceleration and is very close together, following the same trend. Same for velocity. And it's good to note that we have taken areas, we have discounted regions where it's externally affected by magnetic force, but the whole data represents the external magnetic force. So therefore, as we do the integration the second time to get displacement, you can see that, yes, there is a slightly more variance as we keep integrating, but the trend is still very, very similar. Thank you for watching.
And this was our experiment. For our experiment, we wanted to design a catapult using chopsticks, which would be used to launch a coin. Here are some materials and equipment we used. We used a chopstick, which was 27 centimeters in length. And it weighed 18 grams. The coin being launched was 23 millimeters in diameter, 2.74 millimeters thick, and 8 grams in weight. And the weight of the lid, which holds the coin, the weight can be ignored since it's negligible. Here we show the catapult in action. Now the purpose was to determine the angular acceleration and the force and the angle of the force applied to the catapult. Here we have a slow motion recording of the launch. We then use the tracker to track the motion of the coin as it flies through the sky. This is the X and Y displacement data we recorded against time. The X displacement graph was linear because air resistance was negligible. However, the Y displacement was not due to the acceleration from gravity. So to calculate it, we use the graphs to find the initial velocities and use that to find the launch angle. And then we use those values to find the angular velocity and acceleration, and then an equation of the moment of inertia to find the force and the angle the force was applied at.